Okay. So the questions I asked you to take a look at were for the polynomial f of x equals x cubed minus 6x squared minus x plus 30. I asked you, is x plus 2 a factor? And separately, is x minus 1 a factor? So how did folks approach part A?
We use synthetic division.
Okay, so it looks like some folks did synthetic division, some folks did long division. So we're going to actually stick with the synthetic division. Okay, so if we were to set up our synthetic division, then we know visually we need sort of like this right angle situation over here, and then we have like a whole string of numbers out to the right hand side of that. What number goes inside that little right angle thing for part A?
-2.
It is -2. All right, so we're going to put a -2 in here. And if we kind of scroll back up for a moment, this -2 comes from like what makes our factor equal to 0, right? So when it was x minus 2, we put a +2 there. But since we have x plus 2, we can go ahead and put a -2, okay? And then we need to line up all the coefficients, right, next to it. So the coefficient for the x cubed is 1, and then we have -6, and then we have -1, and then 30, okay? But remember, there were a couple examples that we did in the video where we might need at times a placeholder if there's a power that's missing. So we want to make sure every single power is represented, and if it's not physically in our polynomial, we need to keep its place with a 0, okay? So we skip a line, we draw a line, right? First thing, we bring that 1 straight down. And then what do we do when we are combining the -2 and the 1? What math operation are we using?
Multiplication. Yes. Multiplication.
Yeah, we're multiplying those, okay? So -2 times 1 will give me -2. And then what do I do this way?
Addition.
Addition, exactly. So -6 minus 2 is -8. And then we keep going. So we multiply. So we get 16. And then we add, which gives us 15. And then we go one more time. -2 times 15 is -30. And we add, and we get 0, okay? So that's the basic process of synthetic division. But what's more important for me is that we understand what all these numbers mean, okay? So talk to me about what these different numbers mean and how we can interpret our results here. And by talk, I mean chat is fine too. So what's the significance of our answers?
By successfully factoring it, you end up with a quadratic, and you can tell because if you start off with a function that has x cubed as the greatest degree, if you were to factor out anything that has x with something, that automatically, and it successfully works out, that makes it x to the second power as the next highest degree. So then you're able to have a quadratic and then break it down any way, which way you want, whether it be quadratic formula or factoring or any of those. And then you can have all your factors.
Perfect, perfect. Yeah, so we have at the end, and I think Nitan says this pretty well here. He says 0 is your remainder, right? So we're dividing these two, which is what Richard was saying, right? We're taking this x cubed something, something, something. We're dividing it by an x plus 2. And when we get to the end, we have a 0, okay? Now that last number is super, super important because this last number is our remainder. And we mean remainder the same way we do when we divide regular numbers, okay? So if I divide 3 by 2, what's the remainder? If I divide 3 by 2, I'll get a remainder of 1, right? So another way that we might think about that, yeah, is that 2 is not a factor of 3. But when we get that the remainder is 0, what that tells us is that x plus 2 is a factor of f of x. Okay. Now, more significantly, it tells us it's a factor, but it also tells us the other factor, okay? So the 3 numbers that we have here, the 1, the -8, the 15, those stand for coefficients, okay? So this 15 is just the constant, but this -8 is really -8x. And this 1 is really 1x squared. Okay, so we sort of build backwards that this first number will always be the constant, the first number after the remainder. The second one will be a linear term. The third one will be quadratic. And if I had more numbers, I would just keep adding a degree. So the next one would be cubic, and the next one would be to the 4th degree, and the next one would be to the 5th degree, okay? So we can keep building on this to get all of those coefficients. Now, we won't see that in this class. I really want us to focus on the cubic case so we really master that one, okay? But what we can say, given all this information, is that x cubed minus 6x squared minus x plus 30 can be factored to be x plus 2, because that's the orange one we got in the beginning, times x squared minus 8x plus 15. Okay. If it's helpful to you, you can throw a +0 on the end. That +0 is our remainder. All right, how did we change our setup for part B?
There's a 1. Oh, sorry.
No, go for it. Go for it.
There's a 1 that's the 1 goes in the corner.
Yeah, the 1 goes in the corner. Yep, same thing from Eric. That's going to be a 1, right? And that's a 1 because what number goes in x minus 1 to make it 0? And it's a positive 1, okay? Now, the coefficients should be the same. 1, -6, -1, and 30. We skip a line, we draw a line, and we do the same thing that we did for part A, just with a different number. So we drop the 1 down. We have 1 times 1, which gives me 1. We add, and that gives me -5. We multiply 1 times -5, we get -5. We add, we get -6. We multiply 1 last time, we get -6. And when we add, we get 24. So how does our interpretation of this change from part A? Like, what do our results in part B tell us?
It is not a factor.
It is not a factor. Okay, good. All right. So when we get to the end, that last number is our remainder. Okay, that part does not change. It's still a remainder. But because this number is not equal to 0, we know that x plus 1, x minus 1 is not a factor of f of x. Okay? If the number at the end is a 0, then we're good. It's a factor. But if that number at the end is not 0, it is not a factor. Okay? Now, if we go back to the notes, okay, if we get not a 0, then what I want you to identify is tell me what your remainder is and tell me what your quotient is, okay? So if we go back down here, we have our remainder of 24, but our quotient is going to be these three numbers right here are going to help us figure out our coefficient for the quotient, okay? Just like the last example, it's going to be x squared minus 5x minus 6, because that last one is a constant, okay? And there we have it, our remainder and our quotient. All right, any questions on the process of synthetic division?
So when the remainder is not 0, we don't add it to the end of the quotient, like how earlier you put plus 0 at the end.
Oh, okay. So this is only this part right here is the quotient. Like this x squared minus 8x plus 15. So if I wanted to write it the same way I did above, I could write that this polynomial is equal to x minus 1 times x squared minus 5x minus 6 plus 24.
Oh, okay.
Okay, so it's like this orange times the green get us close to our polynomial, but then we have to add 24 to get there. Okay?
Okay, thank you.
You're welcome. Yes,
For
go
the
ahead.
quotient, for like the 3.5 notes, example number 7, did you divide it by 2 because it was 2x minus 3?
Yes, I did.
Oh, okay, okay, thank you.
Okay.
The 2x, yeah.
All right, any other questions? Okay. So we're going to go ahead and jump right into 3.6, okay? So if you go to the 3.6 notes, all right, it should look something like this. And that polynomial f of x should look super familiar, right? We just took a look at this particular f of x cubed minus 6x squared minus x plus 30, okay? So now 3.6 is really where I would make sure to study for exam 2, okay? A lot of the stuff that we've been learning in 3.3 and 3.4 and 3.5 all come together in 3.6. So if you want to study like almost like backwards, if you study 3.6, I bet you're going to find that you don't have to spend as much time on 3.5, 3.4, and 3.3, okay? And I think it will help you prepare for the types of questions that I'll ask on the exam. On the flip side, if you choose to study 3.3 and then 3.4 and then 3.5, and then you kind of get tired and you're like, well, I'm sure 3.6 will be fine. I'm not sure that's going to serve you quite as well, Okay, so you're welcome to go from 3.3 all the way through 3.6, but the big message here is please, please, please make sure you study 3.6, okay? All right, so with that, let's go ahead and get started. So given this polynomial, let's talk about some things that we learned in the other sections. So for parts A, it says determine the degree and leading coefficient of the polynomial. So what do we have for the degree and the leading coefficient of this f of x?
3 is the degree and the leading coefficient is 1.
Yeah, exactly. So we have a third degree, okay? And that third degree is because we have it in standard form, so we pick the highest degree. So we have it in standard form, so pick the highest degree. Okay, we don't have to add any of the powers together because they already multiplied it out for us. And our leading coefficient is a positive 1 because that's the number in front of x cubed, okay? Now this, if that doesn't sound super familiar, for part A, I would go back to section 3.3 and you can read and redo some problems on degree and leading coefficient, okay? All right, let's talk about the end behavior of this polynomial, all right? So the end behavior of this polynomial, are the ends going to match, like they're both gonna go up or they're both gonna go down? Or are they going to be different?
Different.
Yeah, they're gonna be opposing, right? So now the question is it going to be down, up, or is it going to be up, down? All right, it is going to be down, up, exactly, okay? So we're gonna end up with down, up because it's an odd degree and a positive leading coefficient, okay? All right, last review-ish piece, determine the y-intercept. How do we find the y-intercept? Don't just tell me what it is, tell me how we find it.
Find f of 0.
Yeah, we're just gonna plug in 0 everywhere we see an f. Now, I know a lot of us can do these computations in our head, but this symbol right here, like this notation, f of 0, tells me that you understand how to find the y-intercept, okay? And you can even just say, all right, I'm just gonna plug in 0 here. And at the end, we get 30. But we wanna make sure we write our coordinate. So 0, 30. Okay. All right, any questions about these parts A, B, and C?
What's the LC plus 1 on the A box?
For sure, that is the leading coefficient.
Oh, okay, thank you.
You're welcome. Okay. Any other questions about parts A, B, and C?
Oh, do you always have to set the f of x to 0? Or was it just for this example, for C?
That's a really good question. So let's clarify some things here. We're not setting f of x equal to 0. We're setting x equal to 0.
Oh, okay, okay.
Okay, so anytime you want to find the y-intercept, that means x equals 0.
All right.
Okay,
Okay, thank you.
you're welcome. Okay, so we're going to answer these questions for every example that we do today. So hopefully it'll be a good review for some of the earlier sections that we've taken a look at, okay? For right now, we're going to move on to sort of this next big table here and spend some time filling that out, okay? So here's what I want us to do. For these questions, by and large, I'm going to give you the graph of the function, okay? So we have the graph of the function. We can see that our y-intercept matches with the one that we found above, okay? But what our big question is going to be is, what are the x-intercepts, all right? Because these x-intercepts are going to help us find the factorization of our polynomial, okay? Now, some of you on, I think it was quiz 6, went ahead and answered the last 2 questions, which I said you didn't have to answer, okay? And for some of you, you took the polynomial and you did synthetic division like a bazillion times for a lot of different numbers, okay? Now, one thing I want to talk about is there's actually only certain numbers that you really need to try when you're trying to figure out, is it a factor or not, okay? And so in order to answer that, we're going to go back to our original polynomial, all right? And we're going to take a look at the very last term. So in our case, that's a 30. So we've got 30, okay? And we're also going to take a look at our first term, which is x cubed. And what we're going to do is, it turns out that we don't need to try every single number in order to see if it's a 0 or an x-intercept or not, okay? Instead, what we can do is take our factors of the constant, and then we divide them by the factors of the leading coefficient, okay? And then we actually consider all the positive and negative versions of that. So for this particular problem, okay, my leading coefficient is 1. So the only way I can make 1 is just 1 times 1. That one's not very exciting, okay? But how can I make 30? Give me pairs of numbers that multiply to make 30. All right, so we've got a 3 and 10. Good. What else? 2 and 15. Good. What else? 6 and 5. Good. What else?
One in 30?
1 in 30, yeah. So easy to forget that 1 times that number is always going to give us the number, okay? I think that's it, right? There's no more pairs of whole numbers that make 30. Okay, so it turns out that if we tried 1, 2, 3, 5, 6, 10, 15, and 30, those would be the only rational numbers that we need to try. So I would not try 7, I would not try 8, I would not try 1, oh no, I would try 1, I wouldn't try 18, I wouldn't try 19. So it kind of takes a world where there's a bazillion numbers to try and narrows down the field for us, okay? But let's kind of use this information and our graph to help us understand which numbers we should try, okay? So let's take a look. The first time this graph crosses the x-axis is at -2. Is -2 one of the choices from this list that we have here? I mean, 2 is on our list, but remember, it could be plus or minus. So -2 is okay. Well, that's at 3. The next time this graph crosses the x-axis is at x equals 3. And we have x equals 3 right here. So we've got the 2, we've got the 3, and the last time this graph crosses the x-axis is at 5. I would not try any of the other numbers because I know that given my picture, the only 3 that match up from my picture and my list is a +3, a +5, and a -2. Okay. So let's go ahead and use this next part to talk about one of the zeros and the factor. Okay. And in fact, let's use the example that we did in our warm-up. So one of the times where the graph crosses the x-axis is at x equals -2, okay? X equals -2 is the solution for x plus 2 equals 0. So all I did was take this -2 and move it to the same side as the x. Okay. So what we can say is if x equals -2 is a 0, then x plus 2 is a factor. All right. So for those of you who like word explanations better than symbols, this sentence might be helpful. If x equals -2 is a 0, then x plus 2 is a factor. Now, part F over here says use long or synthetic division to confirm that the 0 is indeed a 0. Well, this is exactly what we did in that warm-up activity when you were in your breakout rooms. We took the -2, we put it inside the corner. We lined up our coefficients, 1, -6, -1, and 30. We did our synthetic division. We got 0 at the end. And these numbers represented x squared minus 8x plus 15. I think it's positive. Oh, yeah, I see what you mean. Yep. Like that. Okay. So we got 0 at the end when we did synthetic division. Not only did we find that it is a factor, but we found the other factor. Okay. All right. So let me zoom back out for a moment and just kind of talk about this in the big picture again. Okay, so when someone wants you to factor something, you don't want to just keep trying every single number because there are an infinite number of numbers. So we want to limit our search. Okay, and so in this class, we're going to use this list of possible rational zeros. And we're going to use it with the graph to guess potential zeros for the polynomial, okay? So we chose this x equals -2, and using synthetic division, we were able to show that it is a factor, and we were able to find the other factor, okay? Ooh, okay. Are most folks back on?
I think so. We connected after like 10 seconds or something. But
Okay.
yeah.
Sorry.
You're fine.
Thank you for letting me know.
Yeah, of course.
Okay. So let's for a moment go back to what it means to factor, okay? So let's pick 30 because we've been working with this number. So way back when you were learning about factoring, you guys did like factor trees, yeah? Anybody remember those factor trees? And so you might think like, okay, what two numbers make 30? And you might be like 2 and 15, right? And then to get down to the prime factors, you just kept going for each one, right? So 15 broke into 3 times 5. And so you could write 30 as 2 times 3 times 5 because those were sort of the ends of all the branches, so to speak, okay? And so as weird as it is, we're actually doing the same thing, but instead of numbers, we're doing it with polynomials. So we've got x cubed minus 6x squared minus x plus 30. And so far, we found that it breaks up into x plus 2 and x squared minus 8x plus 15. That's what we found so far, okay? So we took our polynomial, we broke it into 2 factors. Now, why did we stop here with that 2 when we were factoring the 30? How come we didn't keep going?
It's a prime number. You can't go lower than that.
Yeah, it doesn't really factor anymore, right? The only way we could do anything with it is just break it down into 2 times 1. So we kind of just stop there, okay? But using similar reasoning, we did not stop at the 15 because we could still continue to break down 15 into its prime factor. So when we look at our polynomial, this x plus 2 is kind of like our 2 for the 30. Like we can't break down x plus 2 anymore. But let's see if we can break down x squared minus 8x plus 15, okay? And here's how we're going to do this. Let's go back to our graph. Tell me another 0 that I could try. Oh, thank you. So we tried -2. What is another guaranteed 0 of this polynomial? Sorry, Richard, I think I missed what you said.
3.
3, yes, okay, sorry. We have this next door neighbor and their dog barks like all the time, but I feel like the dog has been barking like more lately and like all throughout the night. It's been very disturbing to my sleep. But yes, it is a 3. Okay, so let's see if we can get this all on one page. Okay, so if x equals 3 is a 0, then x minus 3 should be a factor. Okay, so we can write that in words. If x equals 3 is a 0, then x minus 3 is a factor. okay? So what we're gonna do is we're gonna put 3 inside the corner for synthetic division, okay? So 3 goes in the corner. I don't know why I was having trouble describing like how to say like 3 inside the corner, but that word corner makes so much sense to me now. Okay, so 3 inside there. However, you remember how we already factored it into x plus 2 and this x squared minus 8x plus 15? Let's use these coefficients for the second synthetic division. So instead of using 1, -6, -1, and 30, we're going to use 1, -8, and 15. The reason why we're going to use this one is because we don't want to do more work than we have to. And if we factor x squared minus 3x plus 15, then whatever we get here and here will be our factors. And then we'll have all of our factors kind of like we had the 2, the 3, and the 5, okay? So I'm going to go back up here. We're going to use 1, -8, and 15. Drop a line, skip a line, drop a line. Okay, I'm going to bring down that 1. I'm going to multiply. 3 times 1 gives me 3. I'm going to add. -8 plus 3 is -5. I'm going to multiply. I get -15. And when I combine those two, when I add them, I get 0. All right. So we know that when we get 0 at the end, that is a really, really important step because that means that it is a factor, okay? But check out what we've done. We found that x minus 3 is a factor, but what does this tell us about the other factor? Like, what is the other factor?
X minus 5.
X minus 5, yeah. So when I go back down to my little picture here, I can say that x squared minus 8x plus 15 breaks up into x minus 3 and x minus 5. And so what this really tells me is that this polynomial is equal to x plus 2 times x minus 3 times x minus 5. Just like 30 equal 2 times 3 times 5. Okay. Now, Ethan, you bring up a really great point. Can't we just factor after it's a quadratic? For sure, you can, okay? And I just wanted to show this to us so that we could kind of think about how we can use synthetic division in a way that's more efficient. Because sometimes people go back to like the original polynomial in that second step, and all it shows us is that it's a factor, but it doesn't actually help us find another factor. The other nice thing about this is actually another way to think about factoring. Okay, so I did not make a video about it, but this could be a way to help you factor if you find that more useful. Okay. All right, so let's add some more vocabulary on here. It says, write the polynomial in linear and irreducible quadratic factors. Now, in this case, we do not have any irreducible quadratic factors, but we might in some of the other examples, and I'll talk about what that means when we get to the other example. So for part I, we can say that after we used synthetic the first time, we got x plus 2 times x squared minus 8x plus 15. Okay? So we have a linear factor and a quadratic factor. Now, if this quadratic factor is factorable, then a linear factorization is just going to be the whole line of all the linear factors, right? All those x plus 2, x minus 3, x minus 5. Okay. Now, in some of the other questions we're going to look at, these sometimes have i's in them. So when we talked about complex numbers, that's going to come back in a little bit. Okay, so sometimes they have i's, and sometimes we need the quadratic formula. And let's write that here. X equals negative b plus or minus the square root of b squared minus 4ac over 2a. Okay? So sometimes we have i's and sometimes we need that quadratic formula, and we'll take a look at examples that do all of those, okay? But as you can tell, these questions are pretty long, okay? So they're pretty long. I would say that as you're studying, doing a few of these will really help solidify all the stuff from 3.3 all the way to 3.6, okay? That being said, we're actually going to take a break right now. So it is almost 10:50, okay? Let's be back at 11 o'clock, and then we're going to take a look at some theorems. So we're going to formalize some of the language we've used, but mostly we're going to spend the rest of the time doing 1, 2, 3 more big practice problems, and then 2 more shorter ones, okay? So I'm gonna stop sharing my screen. We're gonna share my screen. Okay. All right, so some theorems, okay? A lot of times textbooks and instructors, they like to lead with the theorems because these are names for things. But one thing that I wanted to do is kind of flip it backwards, because I think sometimes when we think about the concept and then we put the name on it, it actually makes it a little bit easier to remember, okay? So in the last problem that we did, we actually talked through a few theorems. All right, the first one we covered is the factor theorem. Okay, so according to the factor theorem, k is a 0 of f of x if and only if x minus k is a factor. All right, so k is a 0 of f of x if and only if x minus k is a factor of f of x. So if we think back to when I said, hey, if x equals -2 is a 0, so in this case, k is like -2, then x minus -2 is a factor. And we had written that as x plus 2, right? So this factor theorem is really important because if we know where the graph crosses the x-axis, then we actually also know a factor of the polynomial we're looking at, okay? So another example might be this. Let's say if x equals 4 is a 0, then what is the factor that goes with it? Okay, if x equals 4 is a 0, what is the factor that goes with that? Yeah, in this case, k is 4. So x minus k would be x minus 4. Okay. Let's try 2 more. If we have x equals -3, what is the factor that goes with that 0? X minus -3, good. Or we could write that as x plus 3, okay? Let's maybe write it out the way you said it first. X minus -3 or x plus 3 is a 0, okay? Let's do one last one. Let's say x equals 1/2. If x equals 1/2, what is the factor that goes with that 0 or with that x-intercept? Yeah, we can just keep it x plus 3, Richard, that's fine. Yeah, so if x equals 1/2 is a 0, then x minus 1/2 is a factor, okay? But what happens if I take this whole factor and I multiply by 2? What do I get when I multiply that by 2? (2x minus 1), good. So if you watched the 3.5 video, then you know we talked a little bit about this coefficient thing, okay? So sometimes if it's a fraction for our 0, the factor is actually like if you got rid of the fraction, that's actually the factor, okay? But again, we'll do a couple examples like that. All right, so the factor theorem, just a fancy way of saying something that we already knew, which is that if x equals a number is a 0, then x minus that number is a factor of f of x. Okay, so the other theorem that's important in this section is the rational zero theorem, okay? Now, some people call this the rational root theorem. And that's the same thing because a 0 is the same as a root. Okay, so the 0 is the same as the root. And they both mean x-intercept. Okay. In fancy mathematical terms, the rational zero theorem states that if you have a polynomial that has integer coefficients, then every rational zero has the form p over q, where p is the factor of the constant term and q is the factor of the leading coefficient. And so that's what we did earlier on when I said, let's list out the possible rational zeros, okay? So the factors of the constant go on the top and the factors of the leading coefficient go on the bottom. All right. And together, this list plus the graph helps us choose wisely what zeros we want to try synthetic division with. Okay. So if we go back down here, the p in the p over q, p is a factor of the constant term. Excuse me. Excuse me. And q, thank you. Q is the factor of the leading coefficient, a sub n. Okay, so in fancy words, all it's telling us is that we take the factors of the constant and we divide it by the factors of the leading coefficient, and that gives us a smaller pool of numbers to choose from. Okay. Yeah, but she said it in all capitals, so maybe she meant it more. Okay. So how do we how do we find the possible rational zeros? So we're going to determine all the constants of all the factors of the constant term and all the factors of the leading coefficient, right? So again, the factors of the leading coefficient are the yellow, and then the factors of the constant term are the purple, and then we're going to divide those. So purple divided by yellow. Okay. You do need to put a plus or minus in the beginning because we want to include positive and negative candidates. Okay. I'm going to ask us to kind of ignore this last step. That is one other way to do it, but we're just going to use like list out all the possible ones, and then we're going to match them with our graph and see which ones are worth trying and which ones we don't need to try. Okay. All right. So let's jump back into another practice, okay? So let's try example number 1 here. I'll give you a moment to answer parts A, B, and C. So given this polynomial, I want you to determine the degree and the leading coefficient. I want you to determine the end behavior of the polynomial and find the y-intercept, okay? Let's take a couple minutes to answer those. We'll share out some answers, and then we'll walk through another like synthetic division part of it. All right, so parts A, B, or C. Can someone give me an answer for any part, A, B, or C?
Our leading coefficient is 3.
Leading coefficient is 3. Good, very nice. And I'm sorry, did you say the degree as well?
Oh, yes, the exponent is 3. All right, so we have a degree of 3, and we have a leading coefficient of 3. Okay, so here's our leading term. All right, let's see, what else do we have? The end behavior is down, up. Good. So we know that we have an odd degree and a positive leading coefficient. So together, those two tell me the end behavior is down, up. Okay. Good. And what about that y-intercept? What is the process to find that y-intercept?
Finding f of 0.
Setting x to 0. Good. So f of 0. And if you're like on an exam, I would maybe write it all out just in case. Okay, like this shows me that you understand the process. But just a couple things here. I know that you guys know this. Sometimes I've seen people write like 3 times 0 cubed as 3. So they're like 3 plus 9 plus 0 plus 3. Okay. What happened? What went wrong?
Everything. No, just didn't multiply the zeros by the
Yeah, that's not right, and that's not right. The last two terms are actually correct, but really, this is 0 plus 0 plus 0 plus 3, okay? And so we would write our final answer as a coordinate. We know every y-intercept means we plug in 0 for x, okay? It doesn't matter how complicated the function is. You want to find the y-intercept, you plug in 0 for x. That's it, okay? So hopefully parts A, B, and C here felt a little bit more familiar than maybe it did when we did our sort of warm-up problem together, okay? But those are probably some of the important things to go back and study if you're not feeling super confident about those. Okay, so we need to list all the possible rational zeros, okay? So let's see if we can get those on one screen together. So possible rational zeros means I'm going to divide my factors of my constant divided by the factors of the leading coefficient. And we're going to make sure to have the plus or minus cases, okay? So my constant is 3. So what are factors of 3? Just 3 and 1, right? Not a whole lot of choice there. Yeah. Whoa. And if there's not a lot of choice for 3 on the top, then there's not a lot of choice for 3 on the bottom as well. 3 times 1. Okay. Now, because this one has fewer choices, I'm just going to write out like what our options are so we kind of understand how this works. But like one good number to try might be plus or minus 3, because this 3 divided by that 1 makes 3. Okay. What would be another good number to try? 1/3, yeah, because there's a purple 1 on the top and a yellow 3 on the bottom. Okay. What's another number that we should try or could try? Yeah, because we could take the 1 on the top and the 1 on the bottom, or we could take the 3 on the top and the 3 on the bottom, okay? So that's how we kind of use this list. And now from this list, we're going to go ahead and pick where's our 0 on the graph, and that's a -3, which is good because I really have a -3 in here, right? So the picture should match one or at least one of the numbers from our list, okay? Now, I do want to go back and answer the question about the degree comes from the first number only and not from adding all the exponents, okay? So one thing to kind of go back and review is when we have standard form, okay, then we pick the biggest power. That is our degree, okay? So remember in the beginning when I was like, is this standard form or factored form? It's really important that we know the difference because how we find the degree is different for different forms. Now, if we think about factored form, that's like, factored form would be like this, f of x. You see how it's already factored, right? What's the power for this x plus 2? Well, it's a 1. This power is a 1. This power is a 1. If it's factored, then I add them up, right? 1 plus 1 plus 1 gives me 3. But in the original problem, it was in standard form. So I picked the highest degree or the highest power. Okay, So standard form, pick the highest degree. But factored form, you're going to add the powers to find the degree. Okay, does that kind of clarify when you add the powers versus when you pick the biggest one? Okay, cool. So now we know from this one, example 1, that it's in standard form. So we pick the highest one, so we know it's third degree. Okay. So according to our graph here, we have -3 as the only real 0. Okay, this is the only real root, or 0, or x-intercept. So remember, all 3 of those words mean the same thing. So that means for part E, the only thing we want to say is x equals -3 is the 0. What is the factor that goes with that? So we're using the factor theorem here. All right, if x minus 3 is the 0, then x minus -3, or more simply, x plus 3 is a factor. Okay. So if x equals -3 is a 0, then x plus 3 is a factor. And now we're going to use long or synthetic, though I would say synthetic, to confirm that this is a 0, meaning we better be able to plug -3 into the corner, write out all our coefficients, and that remainder better be 0. Okay? So what are our coefficients for this question? Well, 3, 9, 1, 3. Okay. All right, skip a line, drop a line, bring that 3 down. We multiply. We add. Oh, that's okay if we get a 0, okay? Now, we haven't seen that yet, but if you get a 0, it doesn't mean you stop. You still keep going, okay? So -3 times 0 is 0. Add 1 plus 0 is 1. And we've got one last box to fill, so we multiply. -3 times 1 is -3. And we add. And whew, thank goodness, we get a 0. Our remainder is a 0. That means we have confirmed that the point we said was a 0 is actually a 0. Okay? Okay. Questions so far on just parts D, E, and F? Okay. Whoop. Okay, so the yellow part in the denominator for part D goes back to, whoops, our rational root theorem, or our rational 0 theorem. And that theorem says we do not need to try every single number to plug it in and see if it's a 0 or not. We can pick wisely. So we take the factors of the constant term, so the term at the very end, and we divide that by the factors of the leading coefficient. Okay. So if we go back to this particular problem, the constant is the purple 3 at the end. So those factors are 1 and 3. And then the factors of the yellow 3 in the beginning are, yeah, I know they're both 3. The factors of the beginning ones are also 3 and 1. Okay. Okay. So now we're going to finish this problem by writing the polynomial in its linear, and we're at this point where we can introduce a new vocabulary term, okay? So since I know that my remainder is 0, I can write my polynomial as f of x equals x plus 3 That's my factor. What's the other factor that I found? Or one might say, what's my quotient? X, 3x squared plus 1. All right. Okay, good. So remember, these numbers, all of the numbers tell us about our new factor. And this 1 is a constant. The the 0 is the linear term, and the 3 is the quadratic term. And so when we plug these in, we get 3x squared plus 1 as our quadratic factor, right? 3x squared. X squared is quadratic. But here's this new term, irreducible, okay? So before we talk about irreducible, does everyone understand where the 3x squared plus 1 came from? Okay, I've got one affirmative. Okay. Now the important thing here is that green expression is a factor only if the pink number is 0. So if the pink number is not 0, then we can't save it, okay? But this word irreducible, okay? Irreducible means that you have a quadratic factor that has imaginary solutions, okay? Irreducible means you have a quadratic factor that has imaginary solution. And if we think about this right here, okay, I'm going to kind of do this maybe off to the side down here. 3x squared plus 1 equals 0. If I wanted to solve for x, I would subtract 1. I would divide by 3. And I would take the square root. But when I try and take the square root, I end up in a situation where I'm doing the square root of a negative number. That means this quadratic factor has imaginary solutions, which means that 3x squared plus 1 is an irreducible quadratic factor. Okay. All right, so we've done all this work so far. In order to finish our problem, we want to write the linear factorization. That means we don't want a squared, but we want everything to look something like this. We'll have like x minus 1k, x minus another k, x minus another k. All right, so like k sub 1 is different from k sub 2, which is different from k sub 3, but each one of these is linear. And what we're going to see in just a little bit, I know you can't wait, but what we're going to see in just a little bit is that first factor is going to be real. Because if we look back at the graph, and I'll scroll up in just a minute, but if we look back at the graph, we have one place where that graph crosses the x-axis. That's the one in the orange. But there are two other linear factors. We'll do sort of a seafoam green, because these two factors come from the irreducible quadratic factor. And these two are going to be imaginary. Imaginary factors. Okay, these ones are imaginary factors, which means that we do not see these on our graph. Okay, so these are not visible on our graph. Okay. Let me say that one more time. We've got one place where this graph crosses the x-axis. It's at that orange one, or at x equals -3. But since the highest power of this whole polynomial is 3, we need to have 3 linear factors, but not all of them have to be real. We can have one real and 2 imaginary, and that's okay. Right? We can have one real and 2 imaginary, and that's okay. So the question becomes, how in the world do we find our imaginary factor? And what we're going to do is we're going to use our quadratic formula to find k sub 2 and k sub 3. And so I'm going to do this work over to the side. Let's take this, shrink it a little bit. So x equals -b plus or minus the square root of b squared minus 4ac over 2a. And we're going to get our a, b, and c values from this irreducible quadratic factor. Okay. Now, in this case, the b value is 0 because there's no linear term. And so we'll get 0 squared minus 4 times 3 times 1 over 2 times 3. Which means we'll get plus or minus the square root of -12 over 6. Now, to be able to simplify from here is important, okay? So let's think about how we can break down -12. Well, we can break it down into 4 times 3 times -1. And we're dividing this by 6. Which is nice because then we have 2 root 3. Because the 4 we can take the square root of, the 3 we cannot, so we just leave it inside. And the square root of -1, what does that go to? Yeah, it goes to I. So 2 root 3I over 6. Now I can reduce this fraction a little bit. What does it reduce to?
One third, and then you keep the root 3. And can you put the I out of the fraction, or?
Yeah, we could put it next to it for sure. So I think what I heard you say was we have root 3 over 3, right? Because this 2 and the 6 reduce to
Yes.
1/3. Yeah. And then if we wanted to, we could just put the I next to it, okay? And that way we kind of know that's the imaginary part, right? But we want to make sure we keep that plus or minus sign because we know that we don't have just one imaginary factor, but we have two imaginary factors. So one of them is the positive one and the other one is the minus one, okay?
So, would this still work if we put 3x squared plus 1 equals 0?
It does in this case, but if I had a B term, it might not be so straightforward.
Okay.
Yeah? Okay. So our f of x then is our x plus 3. That was our orange. And then instead of 3x squared plus 1, we're going to write x minus this root 3 over 3I, or x minus the negative root 3 over 3I. Okay, so remember how the factor is x minus k. That's why I have the minus sign in there. And then I put in the positive version and the negative version of whatever I got from my quadratic formula. So this is like my x minus k2. This is like my x minus k3. And we could simplify this a little bit to get x plus 3 times x minus root 3 over 3I times x plus root 3 over 3I. Okay. Now, one quick question for you. All right, one quick question for you. If I multiply this all out, what is the leading coefficient going to be? The way I have this written out right now with that bottom line of the f of x, if I multiply that out, what is the leading coefficient? 1. Okay. But what was my leading coefficient for my beginning question, for example, 1? It was a 3, right? So the way it's written right now will not get you back to your original. So you have to make sure these coefficients match each other, okay? One thing you could do is take this factor, or you could take the other imaginary one. Either one is fine. And remember how earlier we wrote something like, oh, if x equals 1/2 is a 0, then x minus 1/2 is a factor. But then we also said that could be like 2x minus 1. We just like multiplied by the denominator. This is a case when we might want to do that. So if I multiply by 3, then this one becomes 3x minus root 3I. And now my leading coefficient will be 3, which matches my original, okay? So this factor times this factor times this factor would be the linear factorization of the polynomial that I started with. All right, how are we doing out there in the cyber world? Yeah, Yitan, we only changed one because if we changed both, then our leading coefficient would be 9, not 3. So here's what I'm thinking. We've got a couple other examples left. Would it be beneficial to do some work in breakout rooms right now? Or are we like, I just want to kind of see another example before we try it on our own? What are we feeling? One more, one more, one more. Okay, 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 cool. Thank you for that feedback. It's very helpful. Okay. So let's go ahead and see which one might be a good one to do. Okay, let's actually, let's do example number 2. I think that'll be a good one. Okay, so here's example number 2. Let's take a moment, read through the polynomial, and then determine the degree and leading coefficient, the end behavior, and the y-intercept, okay? So let's find those 4 pieces of information really quickly. All right, and I think we should be able to determine that the degree here is 3 because it's in standard form already. Our leading coefficient is a positive 2. Okay, degree is 3, leading coefficient is 2. Here's our leading term. All right, the end behavior of this one should be down, up, like most of our other ones that we've seen, because we're focusing on cubic ones, that's why, okay? And then to find our y-intercept, we're just gonna plug in 0 into our equation. We're gonna be really careful that we know this first term is gonna go to 0, the second term is gonna go to 0, the third term is going to go to 0, but the fourth term will give us the number. And so we can write our y-intercept as 0, 6. Okay. Any questions on parts A, B, or C? Good. I hope these start to feel more comfortable for you, that the determining the degree, the leading coefficient, and behavior, and those y-intercepts, okay? All right, so now that we have that, we're gonna list out the possible rational zeros. And in order to do that, we need to find our constant term, which is the one in the purple, and our leading coefficient. And we know we want to consider the positive and the negative cases. So we're going to take the factors of the constant term first, okay? And we're going to divide those by the coefficients of the yellow term, okay? So when I think about numbers that multiply to 6, I get 6 and 1 or 3 and 2, okay? And when I look at the factors of the 2, I get 2 and 1, okay? So for example, one of the possible rational zeros could be a positive or minus 1/2, because I have like the 1 from here and the 2 from here, okay? Now, according to our graph, is positive or negative 1/2 one of the zeros? No, it's not, right? Because our graph does not cross the x-axis at positive 1/2 or negative 1/2. But it looks like maybe positive or negative 3 could be another option. And I get that one two ways. I could do 6 divided by 2, or I could do 3 divided by 1. Is positive or negative 3 one of the zeros? I would say, yeah, I don't see that it crosses anywhere at positive 3 or negative 3, okay? And Eric, you bring up a super good point, which is if you didn't have the graph drawn out, you would have to check them all right? I don't think very many professors really make you do that these days because we do have a graph, so that's not super valuable, okay? But you could, in theory, this was sort of in the good old days where you'd like try every single number and then see which one works. Yeah, exactly. So there are actually other theorems, other cool theorems, like here's the highest number you should try, here's the lowest number that you should try. So there's a lot of logic and reasoning in this. But if we look at our graph, all right, we've got 1, 0 right here, all right? And what about over here? How many zeros do we have there? Oh, 2, 1, 2. Okay. So let's answer this question by taking a look at Desmos real quick, okay? So if you're cool like me, you've got the Desmos app. It's a free app. I would definitely recommend it, but you can graph functions, right? So we can graph the polynomial we had, which was 2x cubed minus 3x squared minus 4x plus 6. So this was sort of like the graph that you had, that I had cut and paste into the handout, right? But sometimes when we're looking at graphs, it's not necessarily, like the picture might not give us the information we're looking for, okay? So when you go into Desmos, all right, if you zoom in here, you can start to see that was pretty tricky because that graph actually goes right under the x-axis for a hot second and then comes back up. So this actually has 1, 2 different zeros over here. And then it has that third one over here. So the one on the left has 1 0, but this one on the right actually has 2 zeros there, okay? Now, I will not do something that tricky to you on an exam, but I did want to bring up this as a point that, like, sometimes you need to make sure that the diagram is helpful for you, okay? And we don't want to make assumptions about a graph necessarily. But based off of the zeros that we see, what would be a good number to try for our synthetic division? Okay, Richard says 1.5, and I would agree because if I click right there, okay, Desmos even tells you that it crosses exactly at 1.5. Now, I know some of you folks like to round. You know at this point that I don't really like you to round because I like us to work with fractions or just take the whole decimal, okay? But when we look at this other zero right here, I don't really want to do synthetic division with 1.4142. That seems like it's a rounded number. I might not, if I round, then I might not get to my proper remainder at the end, okay? So of these two, 1.5 seems like the better choice. But if we zoom back in over here, negative 1.414, that also does not seem like a quote unquote nice number that I want to do synthetic division with, okay? So let's go with Richard's idea of using the 1.5, okay? So we're gonna use 1.5, but we're gonna use it as a fraction. So what's the fraction form of 1.5? It's 3/2, okay? So we're gonna use 3/2 for our synthetic division, okay? So let me go back into the notes. And whoop, we're gonna go ahead. And sometimes it freezes on me. Super fun. Okay, so we're gonna go back and we're gonna use x equals 3/2 as the zero that we want to try for synthetic division, okay? If x equals 3/2, what is the factor that goes with it? Okay, x minus 3/2. Now, thinking back to my original, all right, let me actually just write the original polynomial here. My leading coefficient is a 2. So you know what would be really awesome is if we multiplied this by 2 and we got 2x minus 3. The reason I'm choosing to do this is because I look at the original problem and I know that leading coefficient is a 2. So if I keep my factors, the 2x minus 3, I'm going to already have that leading coefficient. I won't need to worry about it later on. Okay. All right. So now for some fun times doing synthetic division with a fraction. Woohoo! 3/2 goes in the corner. My coefficients are 2, -3, -4, and a +6. We drop a line after we've skipped a line, okay? That 2 comes straight down, and now I need to multiply. And yes, these are fractions, and I expect you to be able to multiply fractions, right? So 3/2 times 2, what does that give us? Six halves, or it gives us 3. Good. So I've got a 3 here. I get to add these two. Remember, it's okay if I end up with a 0 along the way. Okay, it doesn't mean I need to stop. All right, 3/2 times 0, what does that give us? It gives us 0 exactly. It does not give us 3/2. And so we add, we get -4. And 3/2 times -4, what does that give us? Gives us -6. Very nice. Okay, so -6, and we add, and thank goodness we get a 0 at the end. Okay, so we get the 0 at the end. That means we do have a factor. All right, we've confirmed it, we've checked with our picture, and we know that we have this as our factor. Okay. So if we write our polynomial right now as the factors we have one linear factor from the 0 that we guessed. And then in this case, we have a quadratic factor that goes with it. What is that quadratic factor? Okay. So we're getting the 2x squared minus 4. And yeah, I believe you got that from here, right? We've got 2x squared minus 4. Okay. But if you watched the 3.5 video, I made a point about how if we have, I can't remember what color we used, but if we have a coefficient here, that's like a 2, okay, then we actually need to divide this by that coefficient so we don't end up with a weird leading coefficient. So when we divide this, we actually get x squared minus 2. Okay. Yes, yes. So this x squared minus 2 is what's going to go in here. This is our quadratic factor. We haven't determined yet whether it's irreducible or not. Okay. So let's think for a moment. If I have x squared minus 2 and I want to set that equal to 0, well, I could add 2 and I could take the square root. Is that an okay square root to take? Yeah, it is. We can do the square root of a positive 2. But the one thing we don't want to forget is we got to have our plus and minus when we take that square root, okay? So in this case, this is factorable with real solutions. So it is not irreducible. Okay. This is factorable with real solutions, so this is not irreducible. All right, and to finish the question, we want to actually write it out in the linear factors. So we have one linear factor, which we had from our 0. And then x squared minus 2 factors into x minus root 2 and x minus negative root 2. And I got those from here. Okay, so I think it was Yitan, you were saying, like, can't we just solve for x and that'll give us the roots? If there's no b value, then yes, you can do that. Okay. And the only thing you might want to clean up here, so this is our linear factor. This is another linear factor. You might want to write it like 2x minus 3 times x minus root 2 times x plus root 2. And that would be considered your linear factorization of the polynomial. Okay. For sure. So the b value is like if you have a quadratic like 2x squared minus 3x plus 4, a equals 2, b equals negative 3, c equals 4. So if you don't have the b, then you can just solve for x without having to factor. Does that make sense? Okay. All right. So I know that this is a lot. This is why we did not start with chapter 3, but we started with chapter 4. Okay. I know that chapter 4 is much more relatable. We can actually use exponentials and logs in the real world. And I know that this chapter is like very conceptual and talks a lot about, you know, graphs and where they come from and how we write them as linear factorizations. But, and I know there's a few of you out there, if you're gonna major in math, you're thinking you wanna major in math, this is really the proverbial tip of the iceberg. Like in a lot of the higher math, you take this and you go even more conceptual. And we don't really work so much with numbers, we work more with the ideas and the flows that happen. Like, well, if this is the 0, then this has to be the factor. Okay, and how can we apply these strategies to a variety of problems? Okay, so I know it's not as useful in like helping you figure out your credit card bill or how much you're gonna owe for like a loan or anything like that, but you know, this kind of thinking and reasoning is actually also very important to success in math, okay? I mean, I think it's fun, but I'm also a big math nerd. I understand not everybody is. Some of us are to be here to be like in and out, especially the bio majors. I feel like it's like, oh, why do I need this for biology? But this kind of reasoning, I think if you're going into any sort of STEM field, being able to logically reason is so, so important. Yeah. Have you taken abstract algebra? That actually is a course. I didn't know if you were joking or not. Yeah. Yeah, there's some pretty cool stuff out there. You basically prove where everything came from. Yeah. Yeah. Okay, so here's what I'd like to do. Okay, so let's go ahead and maybe, do we feel comfortable going into breakout rooms now, or maybe at least a little bit more comfortable than we did before example number 2? I'm happy to sit and do example 3 again with you. Oh, like when you have imaginary versus when you don't? Hold on, my sharing froze. Okay. So this one, yeah? So I know this is a cubic function, which means that it could cross the x-axis up to 3 times. But when I look at the picture, it only crosses 1 time. So what that tells me in advance is there are 2 imaginary roots, okay? So if there's only 1 real 0, then the other 2 must be imaginary. And so I go through this process, I do the synthetic division, I do the synthetic division, and I get to my quadratic factor, 3x squared plus 1. And when I think about factoring 3x squared plus 1, I can't factor that into real factors. And the way I was able to tell was when I sort of like set it equal to 0 and solved for x, I realized at the end I would have to do a square root of a negative number. That means my linear factors will have imaginary parts to them. Like there'll be i's in them because at some point I'm taking the square root of a negative number. Okay. So does that clarify the imaginary numbers part? If you can't factor it in the reals, that means that you have imaginary, okay? And so when we said the max x-intercepts, yeah, okay, so this is exactly the point. So if I know I can have at most 3 x-intercepts and I only see 1, it means I have 3 x-intercepts, except one of them is real and 2 of them are imaginary because I can't see them, okay? In contrast, this graph, this is also a cubic function. So at most, this graph will cross the x-axis 3 times. And when we zoomed in, we found 1 real root here, and we had 2 real roots here. So in this polynomial, we had all 3 roots were real. So when we got to the end, our linear factorization did not have i's in them. Okay. Now, one more piece of food for thought is that if you see imaginary roots, well, you won't see them, but if you know there are imaginary roots, they always come in pairs. So if you know there's one imaginary root, there's actually a second one that you also know about. Okay. If you know that there's one imaginary root, you actually know there's a second one, guaranteed. Yes, okay. And actually, let's do an example right now that shows why that happened, okay? So we're gonna skip example 3 for a moment and we're gonna go to examples 4 and 5, okay? Okay, so let's do example 4, okay? So example 4 says, write a polynomial function of minimum degree in standard form with real coefficients, whose zeros include those listed below, okay? So right here, I have 5 as a 0. That means the graph crosses at x equals 5. But then I also have 3 plus 2i as a 0, okay? So this is my real 0. This is my imaginary 0. But as Eric's question was just sort of getting at, if we have one imaginary 0, we actually also have a second one guaranteed. And here's what the second one is. If 3 plus 2i is a 0, okay? If 3 plus 2i is a 0, then 3 minus 2i is also a 0. So remember when we talked about complex conjugates? We're coming back to that idea. right? Our whole point behind the complex conjugates was to get rid of the i's. And if I know that I have a polynomial with real coefficients, I can't have any i's in the end after I multiply everything out. So if 3 plus 2i is a 0, then 3 minus 2i is also a 0. The complex conjugate is also a 0, okay? So almost like a buy one, get one free sort of situation. If you get one of the imaginaries, you know that the complex conjugate is also a 0. Does that part make sense to folks? By the way, I think this is probably the most complicated abstract day of math that we've done so far. So if you're like, wow, over the weekend math got real hard, like this is a complicated day, okay? It doesn't mean that I don't expect you to know it. I just am showing you like it's okay. Like it's okay if you're struggling, but definitely go check out Val's tutoring session then if you want some help around this. Okay. So what is this question asking us to do? We need to write our polynomial, right? This requires us to use the factor theorem. So if we know x equals 5 is a 0, what is the factor that goes with that? X minus 5. Very good. Okay. And here we have our real 0 and the real factor. Okay. Well, if 3 plus 2i is a 0, what is the factor that goes with 3 plus 2i? Yeah. Okay. X minus whatever the 0 is. I know that that might be uncomfortable for some of us because it's like, well, there's an I, there's two terms, but this is the factor that goes with 3 plus 2i. It's always x minus whatever the 0 is. So if we use that same reasoning, if 3 minus 2i is a 0, what is the factor that goes with 3 minus 2i? Right? So if 3 minus 2i is a 0, what is the factor that goes with it? No. It's not 3 plus, it's not x plus 3 plus 2i, okay? Anytime we want to find the factor, okay, if k is a factor, then x minus, if k is a 0, then x minus k is the factor, right? So Michelle, when you did x plus, that plus right there means you're not following the factor theorem. You need to keep that x minus, okay? So let's change this to a minus. And then the 0 is 3 minus 2i. So I'm going to change that plus sign to a minus sign. Okay. So where we change the sign is really important. The sign gets changed based off of the 0. So if 3 plus 2i is a 0, then x minus 3 plus 2i is the factor. And if 3 minus 2i is a 0, x minus that 0 is the factor. Does that make a little bit more sense to folks? Okay. Okay. So this is the setup. And from here, we're going to do a lot of multiplying. Okay. So remember in like section 3.1, and I was like, oh, we need to know how to multiply complex numbers. That's because we're going to multiply complex numbers in a different setting, right? So that skill by itself is not necessarily hard, but when we get back to a more complicated problem, we still have to be able to use those skills in this setting, okay? So before we multiply out, let's clean this up a little bit. I'm going to keep this as x minus 5. The thing in the blue circle, I'm going to distribute this minus sign and get rid of those parentheses, okay? When I do that, I'm going to get x minus 3 minus 2i. All I did was distribute the minus sign, okay? Now I'm going to do the same thing here. Distribute that minus sign, and I get x minus 3 plus 2i. Okay. Now, there's a few ways that you can FOIL from here, but I'm going to suggest that we do the imaginary parts first. Because these two came from complex conjugates, it means that we're getting rid of the i's. So if we can clean up the second two first, and then we multiply in the x minus 5, then we won't have any i's to worry about, okay? Now, I'm a pretty visual, like, mathematician, I suppose you could say. So if you ever learned how to multiply this way, this is how I like to do some of them, especially the ones that have like the complex conjugates, okay? So I would write like x minus 3 minus 2i. That's like the blue one right here, okay? And then down the side, I would do x minus 3 plus 2i, and that's the one in sort of this berry color. Okay. Yeah, exactly. Big kids times table. All right. So in this first box, x times x gives me x squared. X times negative 3 gives me negative 3x. And then this one gives me negative 2xi. Okay. Any questions about how I got that first row? Just multiplying x times all of those, okay? But I'm going to go through and do the same thing with the second row and the third row. So negative 3x plus 9 plus 6i plus 2xi minus 6xi. Nope, sorry, minus 6i. And then minus 4i squared. For me, what I like about this is all my common terms are on the diagonal, so it's super easy for me to add them. But let's see what we can combine. I see that negative 2xi and 2xi cancel each other out. I see that 6i and negative 6i also cancel each other out. And so I've got x minus 5 times, what does this simplify to? X squared minus 6x. And then is it 9 plus 4 or 9 minus 4 for the constant? It's going to be 9 plus 4, good, so a plus 13. Okay, so I got the x squared. These made the negative 6x, and then 9 plus 4 gives me 13. Okay. Now you can simplify this step however you want. If you want to distribute or FOIL or use the box method, either one is fine. But if we distributed here, we would get x cubed minus 6x squared plus 13x minus 5x squared plus 30x minus 65. And then all we need to do is clean that up, and we'll get x cubed minus 11x squared plus 43x minus 65. Okay. So when you see directions like this that say write a polynomial of minimum degree and standard form with real coefficient, the trick here is, you know, if you get one imaginary zero, you have to have a second imaginary zero. And that second imaginary zero has to be the complex conjugate of the first one. Cool. Yeah, they do have a use. It's not like, oh, we just don't see them, so like, you know, whatever. It actually allows us to handle a lot more cases, okay? The rest of this problem is just foiling, multiplying, binomials, or using this idea of area, however you want to frame it for yourself. But you do need to be really careful with distributing your signs, and are you combining everything the right way? And the more like organized you can be about your work, I don't want to say neat, but the more organized you can be about your work, I think the easier it is for you to not make small sign mistakes here and there. Okay. Yes, precision and accuracy. And I feel you guys. I mean, I'd be like making all these quiz answer keys in advance, and then I like go to grade your work and I'm like, I totally made my key wrong, and I like made a stupid sign mistake somewhere. So like it happens to everyone, like the sign mistakes, and it does get better the more that you intentionally practice it. Okay. So I know we've only got about 15 minutes left, okay? But what I would like to do is sort of put you folks in breakout rooms for these last 15 minutes. And I think as a group, you kind of have a couple choices. Option number one, you can try and do example 5, which is very similar to example 4. Okay, that's one option. The other option is you can do example 3, which is very similar to examples 1 and 2. Okay, so kind of choose like what might serve your group the best. Did any groups actually try the whiteboard in the rooms? Was that helpful? Okay, cool. Cool. So if your group didn't try the whiteboard, maybe give it a try this time, because I think, as you can tell, like seeing it written is definitely helpful for the understanding piece. And then I know at some point I had sent a message out that said, hey, ask for help, you know, click the ask for help button if you need any support, and it'll let me know that you need support or you need some help. Was anyone able to find that button?
Yeah, it's like in the corner.
Okay. All right. So look in the corner for that ask for help button. That's a good way to let me know that you need some support, and I'm more than happy to pop into there. Okay. So I will go ahead and send you off to those rooms for the last 15 minutes to kind of get a little bit of practice in there. Does anyone have any questions for me before we do that?